In the previous video, we talked about the baseball batter problem, which says a baseball batter hits a ball 20 meters per second at an angle of 45 degrees above the ground. This looks like this graph. It's going to be parabola. Gravity will be pulling it down. And the question asks, how high was the ball at its maximum height? And we were working on using the Polya method because it's not initially clear how would we solve this. So we went through step one. We explored the problem. We drew ourselves a graph. We went through and we found our information. We found that we're going to be going at 20 meters per second, 45 degrees, and we realized we might have to assume some sort of a gravity and assume an initial height that seemed reasonable for our baseball batter. And then we devised our plan, which was to use the kinematic equation with the three pieces of information that we had found. And this is right here, the kinematic equation. 1/2 times the acceleration times the time squared, plus the velocity times the time, plus your h naught. This is a constant for how high you start out at, equals, again, h, but this time a function of t. So we have slight notational tricks going on, but h0 is a constant and h of t is a function. So let's scroll down here and actually try to solve this problem. Let's plug in our values, and we find, okay, well, let's get a nice color here. 1/2 times acceleration is negative 9.8 meters per second squared times t squared, plus velocity is 20 sine of 45. 20 and, well, what is the sine of 45 degrees? We can draw ourselves out a little triangle here. If we see what is the sine of 45 degrees? Well, if we remember, this is going to be equal to the cosine of 45 degrees is root 2 over 2, and so is the sine of 45 degrees. So this is 20 times square root of 2 divided by 2 meters times t plus 1 meter equals the height at any time t. And here, if we do a little bit of simplification, 1/2 times negative 9.8 is negative 4.9. So negative 4.9 meters per second squared t squared, plus, then 20 and 2 cancel out to make 10. 10 square root of 2 meters t plus 1 meter equals h of t at any time t. And you might ask yourself, all right, this is cool. We've got ourselves an equation that can represent our time at any time t. I can't seem to manage to draw a straight line. That it will represent our height at any time t. But how is this useful? Well, if we think about what we've got, this is t, this is h. We can find the vertex of this parabola, right? The vertex, if you've got a parabola going up, it's the minimum point. But if you've got a parabola going down, which is what we have, right? If you throw something up, it goes up and then it goes down. The vertex of this parabola will be the maximum point, which is exactly what we're looking for. And here we can find the maximum point. So, well, let's remember what the vertex is. The vertex of a parabola, in the form of ax squared plus bx plus c equals 0 is equivalent to negative b divided by 2a, not negative 2a, but 2a. So if we apply what we have in our quadratic equation up here, we find that, well, our b is a square root of 2 times 10. So the vertex here, the vertex of time equals, well, negative 10 root 2, divided by 2 times, right here, our a value of negative 4.9 meters per second squared, and this is really here meters. So we find this, and we won't consider units now. We know that this will be evaluating 2 seconds. So we find, okay, well, the 2 and the 10 here can cancel out, and so can the negative signs. So we find that this becomes a plus, this becomes a plus. After the negative signs cancel out, the 2, the 10 goes to 5. So we get 5 root 2 divided by 4.9 seconds, divided by 4.9 seconds. And this here, this should be meters per second. The meters cancel out. The seconds went to seconds. Seconds squared divided by seconds was just seconds. And we have the v of t equals this. And you might say, okay, here's our answer. This is the maximum height of your point. The maximum height of your point, given that it started at 20 meters per second at an angle of 45 degrees, gravity existed, and the baseball was hit at 1 meter of height initially. And you might say, okay, this is the answer, and you might say, all right, I'm done. Let's move on to step 4 of the Polya method. Step 4 of the Polya method is to verify your answer. And step 4 is often neglected, but it is very important. So let's go on. Let's perform our verification on our answer. Well, 5 divided by 4.9 is about 1, and the square root of 2 is about 1.4. So we could say that our answer is about equal to 1.4 seconds. And, well, there are 2 things initially that are very wrong with this answer. First of all, we are giving a measure of seconds, whereas the problem was asking for how high was the ball at its maximum height, its maximum, its maximum height, right? So not only was this giving us the wrong unit, but also if we just consider here 20 meters per second, 45 degrees, it would seem much more reasonable that it would be something more like 10 meters, right? If we go back into our white color here and we draw out our graph, it doesn't make sense, right? Intuitively, it doesn't make sense that if you would be starting off at such a speed as 20 meters per second, then this is like how fast your car is going on a freeway, and you're only dropping by gravity, and you've got 45 degrees. It would make sense that this would be going up quite high, much higher than 1.4 meters per second. So in verifying our math, we've realized that there is a problem with it. This is clearly not the answer. But there is some merit to what we've done, and if we go back and think we can diagnose our problem, we say, okay, we found the vertex of this height versus time graph, and inherently the vertex here was a measure of time. So what we can see is that this is not actually the maximum height, but the time when we reach our maximum height. This 5 square root of 2 divided by 4.9 is actually just how far into the hit, if you count like 1 second, 2 seconds, right? How far into the hit will the baseball be at its maximum height, not the maximum height itself. But this is good news for us, because if we go back to our height of time function, we remember that we were finding height as a function of time. So if we found our maximum time, in theory, we should be able to plug our this vt, let me go back to our yellow color. We should be able to plug in this. Well, let's plug in our, this is like t max. Let's plug this into our height function to find the maximum value for the height. All right, well, if we plug this in, then we'll find, all right, well, our height of t function, negative 4.9 4.9 meters per second squared times our t squared, which is now t max. This is 5 square root of 2 divided by 4.9 seconds squared plus 20. Well, if we go back to this is the equation we're dealing with, our simplified form here. This is the equation plus 10 root 2 times meters times t again. Our t is 5 square root of 2 divided by 4.9 seconds, and this is meters per second, excuse me, meters per second there, plus 1 meter, and this should equal our h max, And if we go on simplifying this, well, what we'll notice is we'll get negative 4.9 times, well, 5 squared is 25, square root of 2 squared is, well, 2 by definition, divided by 4.9 seconds squared. This is 4.9 squared coming from here, divided by seconds squared coming from here, and then times meters times seconds squared from in here. So the seconds squared cancel out, and the 4.9, the power of 2 is reduced to a power of 1, and this here goes away. And then here we add on our second term. We get 5 root 2. Well, 5 times 10 is 50. Root 2 times root 2, as we know this, 2. And we get the seconds canceling out. So we get divided by 4.9 meters plus 1 meter equals h max. And here, let's give ourselves even a little bit more room. Let's do this. Okay, so 25 times 2 is 50, and the 4.9 here, we have a common denominator, so we'll get 50 times 2 is, here, let's do that in a minute. 25 times 2, so this is negative 50, right? We still have the negative sign from this 4.9. Negative 50 divided by 4.9, and this is meters, plus 100 divided by 4.9. This is meters, this is 50 times 2. Plus 1 meter equals h max. And we just combine the denominator, and we find that h max equals 100 minus 50 divided by 4.9 meters plus 1 meter. And if we go back and just do some simplification, 100 minus 50, we could say that this is just 50 divided by 4.9 meters plus 1 meter. And this is our final answer. 50 divided by 4.9 meters plus 1 meter. This is the h max. And if we go back thinking about our verification step here, it makes much more sense to have 50 divided by 4.9. This is about 50 divided by 5 is approximately 10 meters plus 1 meter is give or take 11 meters. It makes much more sense that after going up at 20 meters per second at an angle of 45 degrees, it makes much more sense to me that we would peak out at about 11 meters. This is about 33 feet. About 33 feet is 11 meters. Makes much more sense that we would peak out at about 11 meters than 1 meter. So this here is our application of the Polya method. We began part 1 by exploring the problem. We said, okay, what information did the problem give us? What assumptions might we have to take? And then we found the kinematic equation as a good solution to how we could plan to solve the problem. Then in this video we executed our plan. We solved, we simplified, and we realized that this is really not our answer. This is just the maximum time, the time when our maximum height will happen. And it's good that we performed step 4, verification and reflection. We thought about our answer, and intuitively it made no sense. Not only was it way too low, but also had the wrong unit. So we plugged our maximum time, as we then realized, into our function, and we found our maximum height. And that right there is one application of the Polya method to a math problem.